Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Nikitha Saji with us today. Hi, Nikitha.
Hi, Francis.
How are you today on this
Good.
Friday, November 26, 2021, as we do this
Yeah,
recording?
I'm good. Thank you for asking.
Good. And where are you
Uh,
located at, Nikitha?
so I'm currently based in Copenhagen, Denmark.
Is there snow on the ground yet in Denmark?
Not yet, but we
Not yet.
expect by the end of the week.
Oh,
According
okay.
to the weatherman. Yeah.
Okay.
Yeah.
Wow. Okay. I'm in Phoenix, Arizona, and there is no
Okay.
snow in sight.
Yeah.
Um, uh, but we do get a lot of snowbirds coming down. So we'll get a lot of people coming from Canada on down to enjoy the very mild winters in Phoenix.
Okay.
So we get this seasonal flux of people coming in, and then when it gets a little too warm for them, circa March, they'll go a little more moderate. And what is your position there in?
So I'm a postdoc here.
Cool.
I'm postdoc. Yeah, I work at the Center for Star and Planet Formation.
Okay.
University of Copenhagen. Yeah.
Very cool. Very cool. And how long have you been there at?
So actually, I did my PhD here. I did my PhD here with
Nice.
with my advisor, who's also a co-author in this paper.
Cool.
And then I went away for a bit, and now I'm back here as a postdoc again.
All right. Well, congratulations, Dr. Saji.
Thank you.
Very cool. So Nikitha, what do you like to do for research?
So yeah, I have to say I'm not an astronomer. I am an isotope geochemist or cosmochemist.
Yeah, that's
So my primary research interests are a little bit far from what the APJ like normally deals with. So I study the early Earth. I'm interested in how the Earth formed. By way of that, I'm also interested in early solar system. So that's how I got into this project. So I study everything from early solar system to early Earth to early continents. So I have like a broad range of interests. Yeah. And I use isotope geochemistry primarily for that.
That's great. That's astronomy. It's all good. Very big umbrella. It's a very big umbrella. That then is going to bring us to this very lovely. This one is an APJ letter on isotope dichotomy from solar protoplanetary disk processing of 150 neodymium stellar ejecta. And Nikitha, take us away.
Okay, thank you. Thank you for having me to talk about this paper here. It feels great. So maybe I'll just start by giving you some introduction on what inspired us to do this paper. So this paper is sort of a follow-up on something that we did published in GCA last year, dealing with the neodymium isotopic variability in solar system materials. And we found that we were seeing some really interesting things that could have broader implications for the astrophysical astronomy community, which is why we decided to write this paper and send it to APJL. So we know from a large number of studies now that there is significant isotopic variability between different solar system materials from heterogeneous distribution of presolar dust grains in the early solar system. So there's some debate about like the origin of what is the origin of these variations. We'll get into that towards the end of the paper. But we do know that this exists, but we don't know that much about the inventory of presolar dust populations that were probably present in the early solar system. So if you could scroll down a bit, yes, thank you. So for some of these elements, some transition elements such as zirconium, molybdenum, ruthenium, palladium, barium, etc., including neodymium, which is the focus of this study, we know that these variations can be attributed to dust from AGB stars, which are the main sites of S-process nucleosynthesis. So there's another class of isotopes, low-mass neutron-rich isotopes, such as 48 calcium, 50 titanium, 54 chromium, etc., as well as R-process isotopes of molybdenum that show isotopic variability, and we attribute this to supernova-derived dust. So we know that this exists. As for S-process isotopes, we have identified pure S-process signatures that we know from stellar models in actual pre-solar grains recovered from meteorites. But we haven't been able to do the same for neutron-rich and R-process isotope anomalies. We don't know that much about their carriers at all. So we started out the study by wanting to understand the different nucleosynthetic components that contribute to neodymium isotope variations in the solar system. Materials. So one way to do that for us isotope geochemists is to take a meteorite, subject it to stepwise leaching. We subject it to stepwise acid leaching so that we can separate different pre-solar grains that might have different chemical and mineralogical properties. So that's what we did. So if you could go to table 1, where we show the procedure that we did. So that's what we did, leach steps from L1 to L12. So this is a very detailed leaching step that we did. In some of the studies, like people do like a crude separation with, yes, if you have a question.
Yeah, I was going to ask, when you do
the
leaching on the sample, how much mass is in the sample? Are we doing a kilogram of stuff? Are we doing a nano?
Okay, I just have to refresh my memory. I think in here, could you just go back? I think we do that. We do say that.
How about a gram? Here we go.
Here we do like about 1 gram to 2 gram, but it depends on the concentration of the element that you're interested in. So if you are looking at a major element for calcium, you don't need that much material, but this is a trace element. So you need to have a much more material to to do this.
Okay, very good.
So we did the sequential leaching procedure, and we got these different fractions and we analyzed them for neodymium isotopes. So that's what we did in the study basically. So the idea for choosing this specific sequence of reagents is that you go from light weak acids to strong acids, so that in the first few steps, like L1, it's just water. You just get the most, soluble things out. And then you go to acetone, different, molarity of acetone, progressively stronger nitric, HCl, and in the last 3 steps, we add HF so that you can dissolve the most resistant phases. The pre-solar grains by their nature are, resistant. The fact that they have been preserved in the meteorites for us to study them means that they are highly resistant to any sort of chemical processing. So that's the idea behind this procedure. And yes, so what do we, what do we expect? What did we expect when we started this? So the conventional idea in the community is that neodymium isotope variations can be explained by S-process variations. And we think S-process is fairly much more understood than R-process for obvious reasons. At least that's what I have gathered from reading about it. Yes.
We'll say I won't just...
So at least in the geochemical isotope geochemistry community, that's the idea. We think that we have figured out S-process, something like that. And so because we see that we could see pure S-process signatures that agree with the theoretical predictions for a lot of elements. We've seen that for zirconium, molybdenum, barium, neodymium, samarium, etc. So we have this idea that for these heavy elements, the variations that we see can be explained by S-process variations, except for one another minor component, which is a P-process component, which we don't talk about in this paper. It's a completely different issue. But when it comes to our S-processes, we think we can attribute everything to S-process because we actually see these signatures in like pre-solar grains, highly refractory silicon carbide grains, graphite. So these have all been studied since the 90s, actually.
Yes.
So since very early on, we know that they exist, but we know nothing about the R-process carriers at all. We haven't been able to isolate or measure anything. So when we started this, the expectation was that like we should see S-process anomalies in line with what is predicted by classical models. So if you want to go to figure 1, I guess.
That's one question before we go to figure 1.
Yes.
Why the Tagish Lake was because it was valuable, or?
Yes, exactly. I mean, if I'm being honest, that's one reason. But you could take any primitive, any carbonaceous chondrite. So Tagish Lake is a primitive carbonaceous chondrite. So we were, as a first step, you're interested in carbonaceous chondrites because that's the sort of average solar system. So that's what you would do, like when you try to do this for the first time. If I were to do like a bunch of stuff, I would look at different chondrites, maybe ordinary chondrites, etc. But like as a first step, you would choose a carbonaceous chondrite, and Tagish Lake was a carbonaceous chondrite that we had, a pretty primitive one in that, so that was an obvious choice.
Okay, very good, thank you.
Okay. Yes. So
there's our residues, and we'll go to figure 1.
Yes.
There we go.
Yeah, so I just plot the table 1 and table 2 in figure 1. So it's easy to see what I'm talking about in a figure rather than in a table. So what we look, yes. Can I? Did you ask me something?
No, go ahead.
No, sorry, I thought you asked me something. Okay, so we are, so in this plot, we are looking at the different neodymium isotopic anomalies that we measured in the mu notation. So this is parts per million deviations in these isotope ratios from the terrestrial standard. And so we are looking at 142, 144, 145, 146, 148, 150. These are the 6 isotopes of neodymium that we have studied. We don't do 143 because it has the huge radiogenic component. So we don't, it's very hard to say anything about the nucleosynthetic contribution in that. So I haven't plotted that in this figure. You can also see towards the bottom the main nucleosynthetic process that contributes to each of these isotopes. So for 142 and 144 and 146, it's S-process dominated. 145, 148, and 150 are R-process dominated.
I'm with you.
Yeah. And I also, so the different colors correspond to the different fractions from L2 to L10. So you don't see L1 and L11 and L12, if you remember from the table before here, because they had too little neodymium to be analyzed separately. So we had to combine, so we combined L1 with L2, and we combined L11 and L12 with L10. So that's what we did. And I also plot here the dotted line is the stellar model predictions for S-process neodymium. So what is the pattern that you expect if you were to mix S-process neodymium that is predicted by the classical stellar models with average solar system neodymium? And that is the dotted line here. And I have 2 figures here because we have 2 panels, because when you look at isotopic compositions this way, when you are looking at mass-independent isotopic compositions, which is what we do here, you need to, so the way we measure them on the mass spectrometer, which is dominated by mass-dependent fractionation, so we need to correct for that. And we do that by normalizing the data to a ratio that we know. So you can make your pick. So we can do this with 148 and 144, which is what we do in panel A. Or you can choose 146 or 144, which is what we do here. So this is something that that people have not been able to do in previous studies for neodymium. So we are able to do this because of the specific technique that we use. So we have enough precision on all the isotopes that we can play with the data like this and kind of see what are the effects on the different isotopes. So for 148 and 144, you can see that one is an R-process dominated isotope, and on the denominator, you have a S-process dominated isotope. So you would see R-process effects propagated onto your other, anomalies
Okay.
in figure 1, whereas for, A, and
For
in B, you have 146 and 144, which are both S-process isotopes. So you would see
Oh, yeah.
S-process, variations propagated onto your mu values. So
Huh.
which is why we have like a nice pattern in B, whereas A, it seems a little bit more chaotic, So maybe I can show you B first. So because 140, okay, let's ignore all the like L2 to L6, say, for example, because they have really small anomalies that are really hard to see on the scale. And that's because they're dominated by the average solar neodymium. So they have like about 100 ppm variations maximum from the terrestrial. So it's very hard to say anything about them, but you will see later that they are perfectly complementary to what we see on the later fractions, which is like, say, L10, for example, for many of the isotopes at least. So if you look at 142, L10, which is where we expect the S-process carriers to be present, because that's they're contained in the most refractory phases, and they're dissolved in the last phase, L12. So L10 should have the S-process signature. And that's what we see as well. They have huge anomalies, like up to 3,500 ppm on 142 and down on like 5,000 ppm on 150, in that range.
Yes.
So you see that there is an excess in 142, which is expected because this is an S-process isotope. And you can see there is a deficit in all the R-process isotopes, 145, 148, and 150. So that's what you expect to see for the classical S-process component. But very curiously, what prompted us to write this paper is that you see this deviation on 150, which we did not expect. So you can see that it matches pretty well for 142, 145. You could also say 148 to some extent, but there is something going on at 150 which we couldn't understand. And this is a little problematic also for other reasons, because these are very difficult measurements to make. So there are other analytical artifacts that could have contributed to this 150. So some of the early studies that did these leachate studies observed this, and they also saw deviations on 150, but they were not confident enough kind of attribute it to an actual anomaly. But I mean, so this is a new high accuracy, high precision protocol that we developed in our lab over the course of my PhD that we applied to do this study. So we are fairly confident about these anomalies that we measure.
Question?
Yes.
Wait, so these are coming out of the mass spectrometer. So roughly, what is the size of the error bar here? Are they smaller?
They are too small to be seen in this. So if you can go to the table and see that they are. If you want to go to table 1 or 2,
there we go.
You can see that.
There we go. Yep.
Yeah, so that's the level of, that's the precision that we have. So if you have enough material to measure, your anomalies are, the errors are at the ppm level, less than 10 ppm level. So I will point out to you to L7. So L7 is the fraction that had the maximum amount of no, I'm sorry, L3. L3 is the fraction that had the maximum amount of neodymium. It had about like more than 90% of neodymium is in that fraction.
Yeah.
Yes, and you can see that. I talk about that in the paper. So L3 also deviates from the S-process pattern by about some 80 ppm. And the error bars that we have on 150 are like 5 ppm. So it's hard to see that on the figure because of the scales, but but we can, because of this high precision that we are able to achieve, we can resolve these anomalies really well.
Very cool.
And you can also see, so another test for the same is that you see the same systematics when you do a different normalization. So if we can go to figure 1A, where we normalize to 148.
Yes.
So 148, as we said, is R-process isotope. So for the S-process model, the classical S-process, 148 is, yeah.
Yeah, 148.
Yes, yeah. For the S-process component, you can look at the dotted line. So for a given, so you have an excess in 142 as expected, and you have an excess in 146 as expected because it's an S-process isotope.
Yes.
And for 150, because we are normalizing to 148, they have about like 148 is about 98% R process, or it's pretty close to 150 in terms of relative contribution. So you shouldn't see a huge difference.
We don't.
Yeah. So that was the prediction, but you can see that the anomaly that we measure on L10 is like 1000 ppm. So we clearly have, so this deviation that you saw from that pattern in figure B is kind of magnified, much more magnified. During this normalization. You can see that pretty clearly as a positive anomaly. So this means that there is something there that has a clear 150 neodymium enrichment. So it's not a pure S-process grain that we are seeing there. It's S-process plus a 150 neodymium enriched grain.
Okay.
That's how you could interpret this data. So and this has not been recognized before. So this is like we don't know of any non-classical nucleosynthetic component when it comes to neodymium from pre-solar studies.
Okay.
We know about the P process, but that's a different story and affects only 142, not on this side. So you can also test this on a different way there's another way of looking at it, which is what we do in figure 2.
It's okay. These are 3 isotope.
Yes, they are 3 isotope diagrams. Yes. So if you can see on A and B, so these are diagrams that does not involve 150. So in A, I'm plotting 145 against 148, normalized to 146 to 144. In the brackets, I'm giving the normalization. And so this is the whole range. So the L10 has like 40,000 ppm, I forgot to so the actual anomaly, if you remember in the previous figure, I said 4,000 ppm. Just to fit the scale, I divided it by, so it's actually 40,000 ppm anomaly. If you remember, I didn't point that out. Yes. So the actual anomaly that we measure is 40,000 ppm, which is sort of what you expect. Yeah. So, and in the inset, we show the other ones that have about up to 500 to 1,000 ppm variations. Yeah. So you can see, so the solid line in this diagram is a regression through the whole of the data, which is primarily controlled by L10 because that's the most anomalous one.
Green here.
And yes, and I think the dashed line is the classical model prediction.
Okay.
And the other one is the silicon carbide data from literature. Yeah. The S-process component from silicon carbide. So in these diagrams, you can see that it's more or less a 2-component mixing. So you have the solar neodymium and the S-process neodymium, and most of the data plot along that trend.
Yes.
Yes. So if you could go to B.
Yep.
You see that things are slightly different when you have 150 neodymium in the mix. So in this figure, the solid line again is the leachate regression through our data. The dashed line is the theoretical S-process prediction from stellar models. Yep. And the other line is the silicon dashed dotted line is the silicon carbide data from literature. So the silicon carbide data does agree with the leachates as expected because we are looking at the same thing through different techniques, that's all. So they do agree with each other, but you can see that they clearly deviate from the theoretical predictions.
Yes.
Yes, and you also see that like this deviation is also visible on some other, like you can see L7. So I think it's the orange one,
Orange.
L7,
Uh-huh.
that
Yeah.
kind of plots really, off that trend.
Mm-hmm.
You could, so L7 at terrestrial 148 or 146 values, 146 or 148 values have a clear 150 neodymium enrichment.
Okay.
So we think this is the most pure, component that we could isolate, from our experiment. So this sort of, this is the component we think that is causing this 150 neodymium enrichment. And because it's in L7, which is sort of where you first dissolve the silicates. So this could potentially be a silicate phase, not a very refractory. It's certainly there in L10 to L12, but it's also seen in L7, which means that it's slightly less refractory than the mainstream silicon carbide grains, for example. So
cool.
so
What is MSWD? Some sort of
yes. So this is just a sort of a measure on the how good the regression is. So low values mean that it's a linear regression.
Got it.
And when you have such high values, it means that it's not a two-component system, mixing. Yeah. So, and which is what you see for 150 B and D. Yeah.
Right.
Yes.
Right.
So we know now that, from this data, it was clear to us that there is, okay, I could just talk about figure D as well, where you see the deviation even more clearly.
Yes.
Because the theoretical line is supposed to be more or less horizontal, but you can see the Leachate regression has a clear positive slope.
Yes.
So it's more which is why we think this different normalization helps to really kind of bring out these deviations, which are not that apparent if you just stick to 6x4. They could say that, it's, so that's something new that we could show in this study.
Cool.
Yes, so now we know that there is a 150 neodymium enriched component in this meteorite, and by extension in the early solar system. So the next question was, what is it? Like, we are not nucleosynthesis experts, so we don't know. So we had to do a little bit of amateur nucleosynthesis to understand what it means. So maybe you can go back to the text where it's a little bit easy to see.
Sure.
I think we discussed this in section 3, where we talk about carriers.
No caveats.
Yes, I guess it's just here. Yeah, you can see. So this is sort of where we deal with this. So we have no grain data to compare it to. We don't have like single grain measurements, because all of the silicon carbide data from literature are on bulk grains. So they show the same signature that we see on L10, for example, like kind of a blended signature of S and this anomalous component. So we don't have any grain data to compare it to. And so we looked at models, whether there is something, that could help us understand what the signature is. If you could scroll down, and we found, so one of the ways we understood this is that, so I don't have the chart of nucleides that show the S process, flow here, but so the way we understood this one, so if you can produce 150 enrichment, if you can bypass the branching at 149, which does not happen in the normal S process. I don't know if I could say in the normal the classical S process. So in the classical S process, you bypass 147, which has a half-life of 11 days. So at S process AGB neutron densities, you can bypass that and produce 148.
Okay.
When you have that, I'm not an expert here again. I think it's in the when you have the activation of the 22 neon source, I think you do that. That's one way of doing it. So we convinced ourselves that so if you could with some tweaks in the parameters, if you could have somewhat higher neutron densities that could help you bypass the 149 branch point,
Okay.
you could actually produce 150 neodymium in this way. So we had a number of questions from the reviewers about we had to convince them that this is possible. The cross sections are similar. So I think this is possible. Yes, but we have no data, ourselves to do that. So I think we really do look forward to nucleosynthesis, people who do nucleosynthesis calculations to, I don't know, take this up and tell us if this is possible or not.
Right.
So that would be something we are really interested in seeing going forward.
Yes.
Yes. So in the end, we came up with two scenarios that can possibly explain this 150 neodymium excess. So one was S-process in rotating massive stars. So
Okay.
all of the S-process models that I looked at are Lanterney, Bister, so all of those up until 2015 did not produce 150 in their models. But we found this one paper. Maybe if you could just go back to the previous page.
Okay.
There was just this one paper that showed a tiny production of 150. And that was this Prandos 2019, I think an MNRAS paper that showed a minus contribution from S-process to 150 neodymium abundances when you consider rotation in massive stars. So that sort of told us that's one scenario where you could do this potentially. We know nothing about the yields in starch, but this is a potential mechanism to produce 150.
Cool.
And another scenario that came to us was the Iprocess. So the Iprocess is a very non-classical term, so most people don't even know that it exists. I certainly didn't know until I started reading up on this. So Iprocess apparently operates at an intermediary neutron density between S and R.
Right.
And there are a couple of, it was proposed originally in 1970s, I guess. I can't find the reference now. Yeah, it was proposed very long ago, but then it fell out of fashion and it's back again. I found some few papers recently that talked about Iprocess being able to explain a lot of the features that classical S and R process are not able to. And so given that this is, this happens at, to produce 150, you have to be at neutron densities higher than the classical S process. This sort of felt to us like a natural scenario where this could happen. So and we already have an example for Iprocess in primitive meteorites. So there is a paper from 2014 that identified unusually low 134 barium compositions that was not explained by the classical S process, and they attributed this to branching at 134 cesium, which is not usually activated at in classical S process. So you could imagine something similar happening for the 149 branch point.
Right.
And we also have a prediction. So that's something that we plan to do going forward. So if you actually produce if you actually produce 150 through 149 branching, you could maybe see a correlated effect on 149 because you're producing less 149. And that was some sort of an ad hoc, prediction that we came up with. So these are certainly things that you can look into, and we certainly need more grain data to, and theoretical studies to actually tell us what is this, is this S-process? And another thing that is very interesting to us is that Iprocess, so one of the typical sites that for Iprocess is a super AGB star. So we know that super AGB star that explodes as electron capture supernova, or white dwarfs that explode as type 1a supernova. So for those of us who work in isotope cosmochemistry, these two sources are pretty familiar because we know that the anomalies that I talked about in the introduction with regards to neutron-rich isotopes, 48 calcium, 54 chromium, and 50 titanium, these are the potential sites for generating those anomalies. So that was very interesting to us. So could this be, could these two, signatures be produced in the same signature or not? We certainly don't know. It's an open question, but that's something that we would like to see going forward.
Cool.
So we came back. So in the next section, we kind of come back to solar system again. And try to understand what this means for the planetary scale isotope variations that we see. So maybe I can explain what do we mean by isotope dichotomy.
Okay.
Because that's what we have in the title of the paper. Especially for these neutron-rich isotopes, 48 calcium, 54 chromium, and our process isotopes of molybdenum, we know that there is a certain bifurcation in the distribution in the solar system. By that, I mean the outer solar system materials, where we find the carbonaceous materials, have an excess of these isotopes.
Okay.
Whereas inner solar system materials that we call the non-carbonaceous materials have a deficit of this isotope. Okay. So this is what we mean by the term isotopic dichotomy, that there is a fundamental distinction in the isotopic character of solar system materials into two groups, carbonaceous materials and non-carbonaceous materials. And this is either a very primordial feature of the solar nebula. So there was some sort of a spatial barrier that prevented mixing between these two reservoirs, or another. So that's one model, a popular model these days. Another is that you could, so in these classes of models, you would, so you have supernova-derived dust materials being added to the protoplanetary disk early on.
Okay.
And by a rapid viscous expansion of the disk, you preserved this in the outer disk. Okay. So the carbonaceous materials have this supernova-enriched signature, whereas late accreting materials have a deficit of the signature. So it's a primordial signature that has been inherited from the molecular cloud and has been preserved by Jupiter, for example. That's one model. In another set of models, we can, we explain this by thermal processing or differential processing of the grains due to the difference in disk temperature. So you could imagine that very fragile grains, non-refractory grains, will be lost to the gas in the inner parts of the disk. Okay. So by that way, you could you could generate this dichotomy where the outer materials have the full inventory of presolar grains, whereas the inner disk materials lost that non-refractory component because they were processed. And that's something that you could expect based on the disk chemistry disk models as well. So there are these two classes of models that are currently there to explain this this fundamental feature that we see for solar system materials. So, and when we looked at the 150 neodymium composition of bulk solar system materials, which we show in figure 3. Okay. So we also saw that you can see the signature in 150 as well, which was very surprising. So until now, we have seen that for low mass isotopes, 48 calcium, 50 titanium, and 54 chromium, and nickel as well, and yes, for molybdenum, but we haven't seen that for neodymium yet. So it's not that obvious in the first figure, but I will try to explain that because of the scale. So here we are plotting 150 neodymium against 148 neodymium. Yeah. And the dashed line that I have showed is the theoretical S-process mixing line. So it's not very obvious, but the carbonaceous materials, so the different chondrites, including the Tagesschlag, kind of fall off that line, whereas the non-carbonaceous materials that includes the Earth, Mars, all the chondrites, ordinary chondrites, etc., they plot on either the S line or on top of it.
Yeah.
You know, it's not very obvious because of the scales in that figure. But if you look at the same in figure B, so here we do the same 150 plotted against 146, normalized to 148. You can see that the non-carbonaceous materials have a positive 150 neodymium signature on average, and the carbonaceous materials have a deficit in the signature.
Yes.
You can see that sort of a distinction into two groups based on carbonaceous and non-carbonaceous. It is resolvable. So if you consider the most anomalous end members, so if you consider the error bars, Mars clearly has a plus 10 ppm, plus or minus 3 ppm or something, or 5 ppm. But you can see the, which one was this? It's a CV chondrite, it's a Leander. Or you can also look at a CI chondrite that falls way below at minus 10 about. So this is a difference that we can really resolve at the analytical precision that we have. So we certainly need more data to kind of expand on this point, but it is obvious that you can see this sort of a distinction in 150 neodymium as well. So we could extend this isotopic dichotomy into 150 neodymium now. So this carrier, whatever carrier that we, either the rotating Sprocess or the Iprocess carrier, was differentially distributed between the carbonaceous and non-carbonaceous.
Very cool.
And another surprising thing, so what is shown in figure A in green is not our data, it's literature data. So that's the data for CAI. So CAIs are some of the first solids to condense in the solar system. Calcium, aluminum rich inclusions. You can see that they clearly plot off the strength with huge variations up to 150, 150 ppm, etc. So people have not been able to explain this, what's happening here. On other diagrams, like how we saw in figure 2, like for the other lead shades, they behave as you would expect for S process variations. S or R process variations, but when you on 150, they kind of clearly plot off, and this trend, this fits with the idea that so in most of the other systems, the CAIs are the most extreme end members of the carbonaceous trend. So CAIs have this huge enrichments in 48 calcium, 54 chromium, etc. Carbonaceous chondrites have an excess, and non-carbonaceous chondrites have a deficit. So that's the trend. So we sort of see the same here too. CAIs, carbonaceous, CC, and NC. So yeah. So
cool.
So this brought us to question ourselves, like, how do you do this?
Yes.
So the conclusion, one thing that was obvious to us was that the heterogeneity models that argue for supernova derived dust to be enriched in the outer solar system, they don't work for this because there's clearly a second component involved. So you have to have some very special, invoke some very special scenarios to kind of sprinkle them with the right amount of, things from different sources. Yes. So we think a more natural explanation would be that, so the fact that if they are decoupled, if these two signatures have different sources, you could easily explain this by the carrier properties. So if you could imagine that this 150 carrier behaves differently than the 54 chromium or 48 calcium carrier, you could distribute them in just the opposite way if they had refractory versus non-refractory characteristics. So we think dust processing is a more likely explanation for this dichotomy that we see in the solar system rather than of a springling model, I would say. So that's sort of what we wanted to conclude the paper with. So hence the title, Isotope Dichotomy from Protoplanetary Disk Processing of 150 neodymium rich ejecta, stellar ejecta.
Very
So,
cool.
yeah, that's sort of, yeah.
Very cool.
So this is, yeah, I should acknowledge my co-authors, Martin Schiller, Martin Bizzarro, and Jesper Christian Holst. So Jesper helped me with the digestions. Martin Schiller he works on the protoplanetary disk planetary anomalies quite a lot. So he helped me with understanding the interpretation bit. And Martin Bizzarro is my supervisor, so has been through this whole project. And I should also thank the reviewers and Daniel, who helped me with the lab. So yeah, it's a lot of us who
team project. Very cool.
Yes.
Very cool. Nice results too.
Thank you. Thank you.
Thank you so much for walking us through a very lovely paper. And you mentioned it a couple of times.
Yeah.
Especially toward the end there on pointing toward the future, things that could be done, should be done. So if you look in your crystal ball, let's say over the next couple of years, where does the community go? Or are there additional meteorites that could be leached to look for collaborating?
Certainly, certainly.
Is there new instruments coming up?
So because I work on bulk meteors, so most of the best way to do pre-solar grains is by in situ measurements, which is not what I do. So you have to look at a meteorite and identify single grains and measure their isotopic composition and be able, but the problem with that is that technique is not precise enough to to kind of resolve the anomalies.
Okay.
That has been the problem, I think. So the precision that we can reach based on our solution methods at the 10 ppm level cannot be reached with such methods. So you kind of need to complement these solution-based studies with more rigorous studies, in situ studies that would scan for these kind of anomalies. Now that we know they exist, maybe it's easier to spot them. And I don't think we have spent much time on heavy element analysis for pre-solar grains in the there's a lot of work being done on light.
Yeah.
Yeah, so we haven't looked at heavy elements a lot. So I think that certainly maybe because that's very difficult to do, but we are certainly more advanced than what we were in the 90s. So there are new instruments, of course. So we should maybe try and look in that direction a bit.
Okay.
Would certainly be helpful. And I think we would also like to hear more from the theoretical community, like, what do they think about this? Like whether our classical understanding of Sprocess is insufficient or not, something in that direction.
Cool. Very cool. Sounds like there's going to be a lot of exciting results coming out from this over the next couple of years. Yes. You start putting together, it's sort of like multidisciplinary.
Yes, I think that's the key here.
Right, in finding those colleagues who will, in other fields but related, pick it up and put things together. So very cool, very cool. Nice. Nikitha, thank you once again for taking the time today and walking us through a very lovely paper. And that will do, everyone. And I hope this made your astronomy or your astrochemistry day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you.